All right, good morning. I'm John Hume. I live in Austin, Texas. I work for DRW Trading. I play the drums, and I'm here to talk to you about Clojure internals, and the way I'm going to kind of walk through that is following the life of a Clojure expression. So a few disclaimers before we dive in. I'm definitely not an expert on compilers in general or the Clojure compiler in particular. If anyone here is, and I misstate something or make a mistake and you think you can correct me without being too disruptive, please feel free to do that. If it would take too long, we can follow up afterwards and I'll write up an errata blog post or something. So what I'm going to be showing you is a bunch of Clojure internals, and those could change. I think everything I'm going to show you is pretty stable. Given that there are a bunch of production Clojure systems out there, obviously the maintainers are pretty careful about what changes, and what I'm showing you is right down there in the middle of stuff. But it could all change anytime, so hopefully this talk won't be stale in the next month. And I'm going to show you a lot of code, mostly Java code, not Clojure code. And I've kind of hacked up the excerpts in all kinds of ways to fit them on the screen and ignore things that are sort of annoying details that we can gloss over. But I'm trying to at least remain true enough to what's actually out there that if you go look at the real code, hopefully it'll look a little familiar after this talk. Okay, so what Clojure expression are we talking about? It's this one. So there's this simple function, but the expression we're really going to focus on is this map literal that's the body of this function. It's got two keyword keys and a static or a hard-coded string value, and takes its other val from an argument to the function. So that context is relevant to what we're going to talk about, and I'm going to go a little bit into the details of that context, but at certain points I'm going to hand wave and say, okay, forget about that stuff. Let's just focus on the map, because there's a lot more goes into creating a function than goes into just creating the map at the center of it. And we don't have time, and I don't even fully understand all of it. All right, so really it's the life of that one map literal expression. In the body of a simple function, and I'll talk a little bit about some minor variations, like what might be different if that map were just a constant, what might be different if one of the keys came from an argument to the function instead of one of the values, and what might be different if it had more than 8 key value pairs. Those all kind of take you down slightly different roads. So at a high level, we're talking about the R and the E in REPL. So those things are exposed pretty conveniently in Clojure core read and Clojure core eval, each of which are basically just pass-throughs to Java classes. There's a Lisp reader read method and a compiler eval method. Eval is serious business. It basically breaks down, or the chunks that we're going to spend most of our time on are an analyze phase and then an emit, where you're emitting bytecode. And then we'll talk about what happens at runtime when that simple function actually gets called. So we'll get started. So Clojure core read, as I said, is pretty much just a pass-through. There won't be much more Clojure code than this in the talk. So let's get into the Java. Okay, so this is a few little excerpts from lispreader.java that kind of gives you a flavor of what goes on there. So lispreader has a static array of Clojure, of IFNs, Clojure functions, but written in Java. They're indexed by the character that the reader will see to say, oh, this is what you just ran into, so here's how to handle it. And the one we're most interested in, or the only one we're interested in today, is the map reader. So the index into the array is the char for the open curly brace, and here's all there is to map reader. Obviously, it calls out to some things that are doing some some more meticulous work, but all the map reader has to do is read the list of things that follows the open curly brace until it gets to the closed curly brace, make sure it found an even number of things, and then call this rt_map method. And here's all that is. Takes an array of objects as its input. If that thing's empty, gives you back an empty map. If that thing's 16 or fewer items, that would be 8 entries in a map. Then it gives you a persistent array map via create with check. And if it's larger, a persistent hash map, create with check. Ours is small, so we get into persistent array map, create with check. With check just means make sure you don't have duplicate keys. So it checks to be sure you don't have duplicate keys, and then returns a new persistent array map. And all that does is wrap a persistent array map object around this array of objects. That, what a persistent array map does is creates a map interface with just an array underneath. So at that point, we have an array map. We don't have the array map we're going to have when we call our function. We have an array map of unevaluated code forms. So it's got a keyword, and then a string, and then a keyword, and then a symbol, and it doesn't know what that symbol is. It doesn't know where its value might come from someday. It's just the same thing you would get in the REPL if you just took our code and put a quote in front of it. It's the whole expression, the whole function, you've got a list, and it's got 2 symbols, and then a vector, and then a map. And nothing has happened yet to make any sense of that. But this is important because this is where, so Clojure is homo-iconic. So this is the stage where you're familiar with all these types from runtime, and you can write macros that manipulate this code in any way you like, using those types, the same types you use at runtime, and then continue processing to have the code evaled, which is obviously pretty powerful. So we move on to eval. So Clojure compiler, as I've already mentioned, is serious business. It's a lot to take on. So rather than just jumping right into eval, here's sort of a pseudocode of if you didn't have to worry about a lot of annoying details, here's all there is to eval. You get a form, you macro expand that form, you analyze that form into a compiler expr, and then you eval that expr. So we'll talk a little more about expr, since that's sort of the only new thing here. We're not going to delve into macro expand. So what's an expr? Expr is an interface inside compiler that doesn't have much to it. So you can eval an expr. That means evaluate this thing and give me back the resulting value. That's going to be a value that's going to be the return value of calling Clojure core eval. That's going to be a value you know how to use at runtime, the kind of value you see all the time. An expr can also be emitted. What that means is writing Java bytecode using these various arguments, none of which we're going to talk much about, but we'll talk a little about them. That's a little more, that's the kind of thing you never see at runtime. You almost never have to worry about that as a Clojure programmer, but it's interesting, and it might become relevant to you one day. And then it's got a couple methods about Java classes that the compiler can use to avoid reflection. And where you get exprs from is often, most expr implementations expose a static parse factory method that takes a form of the type that's appropriate for the type of expr. We'll see in a minute how that gets called. For most special forms, there's an interface called iParser that just has a parse method. And and I think there may be only one. I think the fn expr may be the only exception to those 2 ways of creating an expr, but it doesn't really matter, I hope. Or I just decided that. I just decree that it doesn't matter. You have to believe me. Okay. So in the real world, where you have to worry about a lot of annoying details, eval looks more like this. And I've put comments in to sort of it's intentional that this code runs way off the right-hand side because I don't want us to read all the details, but I do want to step through what eval does. And so we can mostly, I think, just read the comments that I've put in there. In some cases, I've just explained the code that's still there. In other cases, I've replaced the code with just a little explanation. So macro expand is more or less the first thing it does. I've chopped a bunch of stuff at the beginning. So now we've got a form that's been macro expanded. The first thing we do is, or that eval does, is if the form is a do, it basically unrolls that do and just pretends all the stuff in the do is at the top level. So it just evals each form and then returns the result of evaling the last form. I couldn't tell you exactly why that special case is important, but I'm sure somewhere in the Git logs it's hinted at least, if not explained. So not interesting for our case, though. So then if the form is some funny little bit of code that's not a def, then eval wraps it in a zero arity function and then invokes that function. And this is also not really relevant to our case, but there's not that much to it, and I think it's interesting to see that, Clojure line compiler could have access to all sorts of weird, private, secret, convenient ways of doing things, but the way that it wraps the top-level random bit of code in a zero-arity function is just to, down here, create a list and make the first thing in the list fn star, and then put an empty vector, and then put the form, and that's how you make a function. That's the same way you make a function in your Clojure code. It's just a lot more awkward because it's in Java. Again, and we eval the results of that, and evaling a function, an fn, is going to give you back a function that you can invoke, so that's what this thing does. And then finally, we get to sort of the standard happy path, where the thing you're evaling, at least when you're evaling your own source files, most of what you're evaling is going to be top-level forms that are defs. And this looks, almost as easy as the pseudocode. You just analyze that form and then eval the expr you got back from calling analyze. So I want to sort of check in on our simple code that we were sending through the system. So that macro expand right at the beginning, depending on how well you know Clojure, you may have learned a long time ago, defn is just a macro that makes it more convenient to define functions, but it just expands into more or less def m, that's our name, and then the fn special form or pseudo special form for our function. So the reason I want to show this is because we're going to focus, as I go through the analyze path, we're going to focus a little bit on each of these things that need to be analyzed. There's the def seek. So when I say the def seek, I mean the list that has def at the beginning of it. Then there's the fn seek, the list that has fn at the beginning of it. And then there's our map, and that's where we'll go into the most detail. The other two I'll hand wave away at a certain point. Okay, so we come into analyze. And analyze basically has this form pretty much throughout. I've removed a whole lot of cases that we're not going to run into in our code, but if it looks at the type of the form, and if that form is a symbol, then there's an analyze symbol method for that. If that form is a keyword, then there's a register keyword to handle that. If it's an instance of iSeek, meaning it's a list, then there's an analyze seek that we'll go into more detail on. If it's an iPersistent map, then here's that static parse method I mentioned. So map expr has a parse method that creates a map expr. And so, in that case, analyze is going to return that map expr, or it's going to return whatever's returned by map expr parse, which actually may not be a map expr. So I'm not going to go into symbols or keywords, but I am going to go into analyzing sequences and the map expr path. So analyze seek, so it's a list. You kind of know what to expect from a list. It's generally going to be you're calling a function. We don't have to worry about it's a macro anymore because we macro expanded already. So again, so I've removed some things, but not actually many things. Whereas this analyze, there are a lot of other things in this big if, else if, else if. Analyze seek, it does some checks for nil. It checks to see if your form is has inline metadata, which I'm not going to go into at any more length, but that's a thing to learn about. And then it says, okay, well, are you the FN special form? If so, there's a special parse method just for FN expr because functions have names that get kind of shoved down into them from the context where they're created. So if you've ever seen a Clojure stack trace, which you probably have, you've probably seen your method names in there. So your method was just deft as a top-level var, but via this name being able to get shoved down in there from the def context, that's why you end up with a class that's named after the var that your function was assigned to. You might intuitively think, how does the right-hand side, somehow the right-hand side of, more or less an assignment has to know that it's being assigned to this name for the class to have that, and def is doing that trick for you. Anyway, we're not going to look into FN expr parse, though. So then we check to see if it's, so FN expr is a special form, or rather FN star is a special form. All the other special forms, if I remember right, all the other special forms are in this specials map. And so we look up in the specials map to see if our op is one of those specials. And our def is going to be in that map. And if it is, the parser that's in that map for def gets called, and that's what gives you back your def expr. We're not going to delve into the parsing of a def expr. And then finally, if it wasn't a special form, it wasn't the FN special form, it wasn't one of the other special forms that has an iParser, then I guess that must be a function you're calling. So you get an invoke expr, and we parse that. We're also not going to delve into that. This is where I wave my hands and say, okay, there's a lot of code that we're not going to look at today, but you'll recall that the pattern was we analyze a form, we get back an expr, we call eval on that expr. So when you eval the def expr, it evals its init expression. That's going to be our function. When you eval the FN expr, it's going to compile a class representing that function the first time it gets evaled. And it's going to compile that class into the dynamic class loader and make it available. So that's going to be interesting, and we're not going to look at all the details of what FN expr does, but we're going to look at what our map expr does when you get there. So each expr in the body of the function is going to be analyzed and then emitted, and so we'll talk about emitting a little bit, but we won't look at the code. So onto map expr parse. You'll recall here, we said, okay, we had a couple of seeks and we went down the analyze seek path. If we had a map, and which we do in the body of our function, we get to map expr parse. So here we are. So I've cut out everything, almost everything but the parse method from map expr, and we'll see the rest in a couple slides, maybe the next slide. So the parse method of map expr kind of just does this little boring dance where, okay, it's got, it has a form, so the form that it's being parsed is the persistent array map that we created back in the reader. So we're going to iterate through that map one entry at a time. Each entry is going to get analyzed into an expr. So here you see each key and value gets analyzed into an expr. And we're going to throw those onto a key vals vector that is the only instance field of map expr. So what we're doing is building up a vector that we can then use to create a map expr. So we get a map expr, and now I've left out the details, but there's some special cases. So after analyzing all the key vals, it runs through and figures out, okay, are all those keys unique, and are they all constants? Are all the vals also constants? And I think it just sets a few booleans to keep track of those things. And then depending on how that all came out, there are a few special cases. So we create this map expr, but then so then the things it checks for that I'm not showing you the details of were, well, is there metadata attached to this map? If so, then it's going to wrap a meta expr around the map expr and return that. If they're non-unique keys, it's going to blow up, but we've already seen a couple of checks for that, so hopefully it didn't happen. Although, actually, sorry, no, that's not true. The checks earlier were looking at the code forms to be sure that they were unique. 2 of those code forms could conceivably have been analyzed into equal values, in which case your keys are not unique, and then you have problems. And then if everything is constant, it's going to throw away this map expr altogether and instead just create a constant expr, and that's going to become just a static that gets loaded at, when the function that it appears in is loaded as a class, that's going to be loaded once, and it'll just be returned when needed. Nothing interesting will happen at runtime. So we return one of those exprs, but in our case, we're going to return the map expr that has our 2. It's going to have, we've got this vector of key vals. It's going to have a keyword expr, a string expr, another keyword expr, and a local binding expr. So the result of the analyze of that argument that becomes the second val in the map will be recognized as a binding to a local, and so now we know what that symbol is going to be for. And so, as I mentioned earlier, the fn expr being evaled will call, as part of writing bytecode for a class to represent the function, it's going to call emit on our map expr. And so now we're going to look at basically everything else that's in map expr. It all fits. So you've got a couple of statics here at the beginning, this map method and map unique keys method. We'll see what those are used for in a second, but so these are ASM. The ASM bytecode library is packaged along with Clojure, sort of repackaged along with Clojure. And these method objects are ASM things, and you can kind of guess they represent Java methods, and they're parsed from a string that almost looks like Java code, so it's just a return type, function name, and a list of argument types. So we'll see how those are used in a second. So emit. So I've left out the details of, you're going to iterate through those key vals, and you're going to determine, are all of those keys constant, and are all of the constant keys unique? And based on those 2 booleans, you're going to decide what to do here down below. So the first thing you're going to do, regardless of those 2, is so this is ASM stuff, and this is what you're generally going to see in emit methods in Compiler.java. So method expr has a static method on it called emit args as array. So it allows you to hand it a vector, a persistent vector of exprs, and it will write the bytecode for putting an array into your method. And now, depending on those 2 flags we set, if all the keys are constant and unique, or if you only had 1 or no key value pairs, then you're going to write a static method invocation. The class is going to be RT, that's Clojure, this RT type is just a constant for the Clojure lang RT class. And you'll use the map unique keys method. You'll call the map unique keys method on RT. So that's this method up above that we saw, the static, one static method at the top. If your keys are not all constant, unique values, then we'll just call RT map. Ours are constant and unique, so we're going to go down the map unique keys path at runtime. And we'll look at that in more detail in a second here. And then this little, this context, I shortened context to CTX, but this little C flag in map expr and in most exprs throughout the compiler is just used to decide if we were in a statement, which is Clojure compiler's way of saying you are an expression in a do, like a function body or a let body or an explicit do, but you're not the last one, then you must be there for side effects or just for fun, but we're going to discard the value. So that's what that gen pop is, just emitting a bytecode to say, throw that away, we're not using it. We are not in the statement context in our method. We're going to use that value. It's going to be the return type of our function. So our map expr is emitted as bytecode. So our function is compiled, and we have, so what's been done, I only showed you the map expr bit, which is the last part of what's on screen right now. The stuff that I didn't show you included some things around static, just writing the class in the first place, and generating these constants for the literal keywords that appear in the code. So what you end up with is the equivalent of this Java code, almost exactly. I guess I renamed the public static final constants to the things that we're using them for. But here's what you end up with. You end up with a class that extends Clojure a function, and it just overrides the invoke method with one argument. And as we just saw in the bytecode emission, it calls rt map unique keys. It passes an object array. It has static constants for those two keywords, so those aren't, there's no interning or looking up or registering of keywords happening at runtime. And that's all there is to it. The one arg to the function becomes the fourth element in the 4-element object array. So now we get to runtime. So somewhere in some other Clojure function, there's going to be some Clojure code where someone calls our m function, passes it a value. Inside that function, there's going to be the equivalent. It will have emitted its own bytecode using a bunch of exprs that I didn't show you. But it'll be an invoke expr. We did see where invoke expr is kind of the final fallback of analyze seek. So that invoke is going to end up generating bytecode equivalent to this little line of Java code, this Java expression. That function will have a static constant for the global var that m has been assigned to. It's going to call get raw root on that var. That's just reading a volatile field out of the var. And then it's going to call that one argument invoke method. The bytecode, it's the invoke interface bytecode, passing that one argument. So map unique keys is going to run, and all map unique keys does is says, okay, if there were no objects, then that's an empty map. If there were less than 16 things, then there are 8 or fewer entries, so we'll create a new persistent array map. And we've already seen what creating a new persistent array map does, almost nothing. Otherwise, we'll create a persistent hash map. And it's maybe not important, but maybe useful to keep in mind as the kind of thing you have to keep in mind when you're looking at Clojure code. This map unique keys being called here, at the bottom here, that's 4-element array is right there in the bytecode. It's always going to be a 4-element array. So map unique keys is going to be trivial. From that call site, map unique keys is going to be trivial for hotspot to inline to just creating you a new persistent array map. It doesn't have to keep checking the size of that array over and over again. It's going to be 4 from that call site. And that kind of thing, that inlining of the checks that you see in the Java methods that underlie the Clojure runtime happens a lot, which is one of the reasons that our code runs fast enough to use. And that's it. And the result obviously is this little map. Apologize. The narrative structure of a talk that's all about what goes on inside, where you're following a sort of trivial function along the way, doesn't end with much of a punchline. But we got our map, as expected. So, what questions do people have? I guess I should look at time, but we're great on time. Yeah.
What was the
Um, the question was, what was the big motivation or the biggest motivation for me to dig into this? I guess there were kind of two things. One was the local user group in Austin was sort of desperate for people to volunteer to give talks, and I thought, oh, this might be interesting. But the other thing was, so I use Clojure in my day job, and it became apparent to me that there were people using Clojure every day, including myself, who, pretty experienced developers who, kind of know their tools or think they know their tools. But there's some really interesting stuff happening at the heart of Clojure, which we were using every day, that we didn't fully understand. And there were cases, there was one case where somebody expressed a concern about the performance overhead of a function that returned an anonymous function or something along those lines. I think it might have been about a call to partial or a comp or something like that. And the concern was, at runtime, every time, we call that thing, a class being created to represent the new function we just created. And I thought, that doesn't sound like probably what's happening. It doesn't seem like you should need to do that. And at the REPL, it's actually pretty easy at the REPL to figure out, like, okay, well, if I call partial several times with the same number of arguments, am I getting a new class back every time? And pretty quickly figured out, no, I'm getting back instances of the same thing over and over again. So that's good. So we shouldn't be worried about that. But it did seem, it was surprising to me that given how long the team that I was working with had been using Clojure, we didn't know the answer to that question off the top of our heads. And so that sort of thing concerned me enough that it seemed like, okay, we should learn about this. Like, we should understand what goes on in here well enough that we don't need to go to the REPL to figure out what is going on. We should be able to look at the code and understand it enough to know, like, yeah, I understand what I'm doing here, right? Am I taking on generating a new class? Am I just taking on creating a new instance of a class that was already generated? The difference, you shouldn't, optimize your code until you've profiled at runtime, but you should know what's going on. And so that's why I felt like it was worth the time and trouble to kind of dig in and start to figure out at least how to find my way around, the Clojure Lang Java package. A lot of it, there's a lot of interesting stuff in there. Just the persistent data structures are a whole, or I suppose, maybe dozens of PhD projects in there. And I don't understand how they work particularly. I understand how they work at I can draw, a few boxes about it, but I couldn't create one. I could probably create a list, but in any case, so, that's interesting stuff. There's also a lot of stuff that's actually pretty easy to follow Java code, but compiler is not among that stuff. Compiler is not easy to understand. And so it seemed worth studying. One thing if you've ever opened up the Clojure Java source in, IntelliJ or whatever, you might notice that it'll tell you a lot of things about, like, oh, this method's not called anywhere, this method's not called anywhere. One of the reasons that it thinks that is because a lot of those methods are called the way that I showed you via ASM bytecode that's generated at load time. And so IntelliJ doesn't know what that method's used for. You can't, the IDE won't help you find it, but it's really important at runtime and gets used constantly, right? On var, get raw root, as far as IntelliJ can tell, is an unused method, but every var reference in your code calls get raw root. It's a really important function. So, IntelliJ is really good at understanding Java code, but even it can't make much sense of compiler. So I think it's something, we should at least feel comfortable kind of peeling back the covers and taking a look at what's in there to figure out what's going on. Yes?
Has digging into this changed the way that you write Clojure at all?
Well, in one kind of small way, so here's a few tangents. If there weren't questions, this is the way to fill a little extra time, although we're doing pretty well. Skipping down to this third tangent, though, it was interesting to me to discover that there's no supported API for creating small maps with compile time constant keys as efficiently as the literal map syntax. So, there's like Clojure core array map, and I wasn't using Clojure core array map all over the place, but it was a surprise. I mean, not a huge surprise, but kind of a surprise to me to find out it's not just wordier, it's also actually slower at runtime. It uses this create as if by assoc method that kind of goes out of its way to, I wouldn't say goes out of its way to be slow, but there's a big comment in there about why it does a bunch of work that you don't think it should be doing. So that was interesting to me, right? Like the literal isn't, the literal is worth using. Like there was one case, there's a library we use where we have a macro for just generating a small map. Like if you have locals A, B, and C, you can just say kvify ABC, and that expands into a map with keyword A, value A, keyword B, whatever. And that was using, I think that was using Clojure core hash map or Clojure core array map, I don't remember. And part of the reason is you pass it an odd number of arguments. Sorry, let me think about this. You pass it, it takes an unknown number of arguments. Those rest args are collected into one local var. And then if you were to try to write a macro that had curly braces and then you just inlined your rest args there, then the reader would read that curly brace and then find your one rest args inlining thing and say, that's an odd number of forms, that's not a valid map. And so it was using Clojure core hash map or array map. And, but it was, suffering at runtime because of that. And so we changed that macro around to just return a map rather than evaluating, sort of using the more awkward way of writing a macro where instead of just syntax quoting something that's just the code you want to run instead, you just create a data structure, and that data structure is going to be what the reader gets as a result. I think that's maybe the only specific thing that's changed as a result of this so far, but at least now I sort of know my way around, so maybe there'll be more in the future. Yes?
Has this work inspired you to start contributing to the compiler itself?
No. But I don't mean that as a joke. I mean, I at no point in looking through the compiler, or there's nothing I can recall offhand where I was like, oh, geez, come on, guys. I mean, obviously, it's a huge Java file. There's a lot of things, sort of obvious suggestions you could make about ways to improve it in some way, make it more, supportable, easier for people to change. But we don't really want people to change it that much, and it does its job. So I would certainly be more, if I found out, oh, look, there's some issue that no one's working on, and it's a really, simple, but it's in compiler, so no one wants to touch it, type bug, maybe I would, try to take that on. I'm not aware of any of those. And, there are people, keeping a pretty close eye on those kinds of bugs and making sure they get addressed pretty quickly. So that's one thing, although this talk might equip people a little bit better to go playing around with Clojure line compiler, I don't want to suggest that, they're hoping to get a lot of pull requests or patches on it, because it's a pretty carefully built piece of code. But if you see an issue, if you run into an issue, by all means, jump in there. Yes. This hasn't changed the way that I write Java, no. I mean, I think, spending some time reading the Java code for Clojure, it does make you kind of reevaluate a lot of the things that, as a Java developer, you consider like this is, the way it ought to be done. Like there are a lot of static methods. In fact, they're almost all static methods, right? I mean, there are also instance methods where it's appropriate, but there's a lot of cases where you don't need an object there. You just need to do a little piece of work on some data. And if it's pure, then a static method's a good place for it. But yeah, I mean, I guess that's kind of all I'd have to say about that. I'm not totally, I don't remember, someone probably has a schedule in front of them. Does the next talk start at 9:50. Okay. Anyway, it is 9:40. I guess I can continue to take questions if anyone else has questions, but I also want to let people stretch their legs and use the restroom. Anyway, thank you.